All right, we're looking at the section 3.5 and 3.6 material. Looking at some new distributions, we've talked about so far the binomial distribution. We've also talked about expected value, and that's kind of a big chunk of what was covered in this first video series for this week. Now we're looking at hypergeometric, negative binomial, and briefly we'll talk about what geometric is as well, those three distributions, plus the Poisson probability distribution and Poisson process. And that will actually round out and finish chapter 3 for us. So if we look at this, and I'm going to talk just briefly kind of about the distributions that we're using as we go through this. So this first one, and I'll explain why in just a second, but it is a hypergeometric. So let's write a little bit about that. So the hypergeometric distribution first thing to note is that the hypergeometric and both the negative binomial, the two that we're going to spend the most time in 3.5 on, they are both related to the binomial distribution. So let's write that down as a little piece of information. Related to binomial distribution, which remember had independent trials, a fixed number of trials, and we had what we call a two-branch system of probabilities, that we have successes or failures. So in fact, the binomial distribution is one that we can use to approximate a model for sampling without replacement from those two branch populations. Now, there are some stipulations for that, provided the sample size n is small relative to the population n. So I'm going to write a little note to the side about the binomial. You'll have to excuse me, I'm still sick. So summarizing that, we can say that the binomial distribution, sorry, I moved my mouse. Is an approximate model for sampling distributions without replacement, so drawing and not replacing, like we did in the binomial experiments, from a two-branch population, which for us has meant successes and failures, essentially. But there's a stipulation or a rule. So when n divided by capital N, and we're going to define both of those in just a second, is less than or equal to 0.05, then you can use, and that's going to be part of this one, the binomial distribution to approximate the hypergeometric. The hypergeometric is actually the exact model for the number of successes in the sample. And we're going to let X, our random variable, stand for the number of successes in the sample. So what are some things you have to be able to do a hypergeometric? So the population or the set of the sample that we're going to be sampling consists of capital N individuals, objects, or elements, a finite population. Each individual can be characterized as a success or a failure. I'm not going to be able to write all this, by the way. And there are M successes, capital M, in the population. A sample of n, small n, individuals is selected without replacement. So big N is the whole population, the finite population. Little n is that sample size that we're taking. and we're taking them without replacement in such a way that each subset of size little n is equally likely to be chosen. Okay, and the notation for this is going to be h of little x, semicolon, n, comma, m, comma, capital N. So that's kind of how we, write what are we doing. We're doing the hypergeometric of the variable x with a sample drawn of size n, and we know that m is standing for the successes in the population. Notice it's capital, and capital N is standing for the size of the finite population. Now this actually has a probability mass function formula, probability of x equal to x, and it's got a lot of combinations in it. It's essentially big M choose little x, so the number of successes in the entire population choose the number of successes in our sample times, and then it's capital N minus M over little n minus x. Notice that if you add this together, essentially those across there, you get big N over n, but you can't really add those. It's just wanting you to see that these are complementary of each other. So this is, remember, those number of failures in the population, the finite population, and this would be the number of failures in the small sample. And then that's all over capital N choose little n. Okay, so that is our formula for our probability. Okay, so when we're looking at this first one, let's read through it. And once I get down to the expected value and the variance part, I'll write those formulas out as well. I just don't have a lot of room at the top. So we have this: a second stage smog alert has been called in a certain area of Los Angeles County in which there are 80 industrial firms. An inspector will visit 30 randomly selected firms to check for violations or regulations. If 32 of the firms are actually violating at least one regulation. So see, we know the number of, we're considering violating a regulation of any kind. We're considering that a success in this case. So we know the number of successes in the 80 population, the population of 80. What is the PMF of the number of firms visited by the inspector that are in violation of at least one regulation? Okay. So we're looking at, excuse me, I'm trying not to cough. We're looking at what are the different pieces that we know. First of all, this is hypergeometric because we have a finite population. There's only 80 industrial firms. We have a sample size that we're going to be drawing, which is the 30. We know that 32 out of the entire population are going to be in violation, which for us is a success. And so the only thing really missing is, out of the 30 smaller ones, how many of those were violating at least one regulation in the sample only. So I'm going to be looking for hypergeometric, so that's H, and we want to make sure we have everything set up. So little population N, that's going to be 30. And then big M is the number of successes in the population. That would have been 32. So that's going to make it this one right here. And then there were capital N, 80 in the finite population. So this is the correct PMF. And again, we would then relate that to this formula for the probability of exactly that. Okay. But right now they didn't ask us to calculate it. They just wanted us to pick the right notation for our PMF. Now for the second part, we're going to do a simpler PMF is what it says. So in other words, they're saying maybe we can use that fact that the binomial model for the binomial distribution could be used to approximate here. So to check this, notice they've increased this quite a bit. Now they said there are 800 firms in the area in which 320 are in violation. So I know my big M and my big N, right? And if you actually look at big M divided by big N, because this is the actual number of violation in the population, This is the total population. That is a ratio of successes over total possibilities. That's going to be a p-value for us for binomial, right? So if we write this down, and we're going to check just in a second to see if this is also true to make sure we can actually do this, that means we could equate this to a p-value of 0.4, okay? Now the question is, can we do this? Can we say, let's use the binomial instead of using the hypergeometric? So the question is this true? Is little n divided by big N going to be less than or equal to 0.05? Well, little n is still going to be that we haven't changed anything about that. This inspector is still going to take a sample of 30 randomly selected firms. So that's going to be 30 divided by the big N, which is 800. And as long as this is less than or equal to 0.05, we feel safe saying that we can use the binomial to approximate what's going on for the PMF. So 30 divided by 800 is 0.0375. So yes, we can use this binomial approximation using the probability of success being 40% of the population is actually in violation of the firms. So remember, the binomial should have a b in front of it, and it's only got two parameters after the x. So binomial is that you have x, and then you have your n, which is your sample size, and then your probability of success. That's the correct format for writing your PMF for the binomial. So this one right here down at the bottom is going to be the correct version. We have our binomial of our variable x is dependent on our sample size n being 30 and a 40% success rate for being in violation. Okay, so now we're going to get down to this point, and they want us to focus on what we gave as our numbers for part B. We're going to be using that 800 firms. So it says let X be the number that are in violation among the 30 visited out of the 800 firms. Compute E of X and V of X. So that's, remember, our expected value and our variance, both for the exact PMF, using those two numbers from that statement up above right there, and the approximating PMF, which was the binomial. Round your answers to 2 decimal places. Okay, so we need to know our formulas. First of all, if you're doing the hypergeometric, your formula for expected value is little n, the sample size, times big M divided by big N, which makes sense. If I expect 80%, this is our p-value when we do kind of binomial, it's n times p still. Now, the variance is going to look a little bit messier. So the variance is our n minus n over big N minus 1. And then we have times n times the big M over n, which is kind of like p. And then you'll see at the end, there's another parentheses, 1 minus m over n, which is kind of like 1 minus p, which is q. So this part should look familiar. This is a little, and you can look at in the textbook to see, you know, how did they come up with that information. We're not going to ask you to prove any of that, so I don't want to spend time going through these proofs for you when you're really just going to be doing computations. So let's look at this. So if we plug in for our exact, we know that for the hypergeometric one, we had h, x, just writing our information down again, sample of 30, m was, for this one, m would have been 320, since we're using the bigger one, and 800, okay? So notice this is n, this is m, and this is big N. Okay, so let's plug in what we know. So for this one, it's going to be 30 times 320 over 800, and that is going to be 30 times 0.4, essentially, which I believe comes out to 12. Yes, so this is 12, and they asked me to round to 2 decimal places, so I'll add 2 zeros. Okay, for the variance on this one, we have big N, which was 800, minus the sample, which is 30, divided by big N again, minus 1. So we'll have that fraction times the, and if you want to just write 12 here, you could, because this is actually your E of X that we just did, the expected value. But if you want to write it out, it's 30 times 320 over 800 times 1 minus 320 over 800. Well, I already know this is going to be 770 over 799. This is 30 times 0.4 times 0.6. It ends up kind of equating to what we saw with the binomial. So we have 770 divided by 799 times 30 times 0.4 times 0.6. I'm just doing that on my calculator. That comes out to about 6.94. It's 938, which would round up to 94. So 6.94. So that's using the exact model, the hypergeometric. So let's talk about that approximating PMF, because we did check, and 30, which was little n, out of big N, which was 800, was definitely less than or equal to 5. But you're going to see it's approximate when we do this part. It's not going to give us an exact. So remember, when we're doing a binomial, binomials, remember, are set up as X, and then you have your N, which was 30, and your probability of success, which we're taking as 0.4. And then remember, we do E of X is just NP, and your variance is N times P times 1 minus P, which is Q. So this is going to be 30 times 0.4. So that's going to come out to 12, like we had for the last ones. Nothing changes there. It's the variance that's different usually. So this will be 30 times the P, which was 0.4, times the Q, or 1 minus P, which is 0.6. And when we multiply that out, because remember, this is an approximate, not an exact for this, we get 7.20. So not as good. And depending on, maybe if our ratio of sample size was smaller even than our 800, we would do a little better. Okay. So that one is complete. Let's move on to number 2. So for this next one, this is a different distribution that's in this section, more specifically in 3.5. If you look at the little WebAssign labeler up here, this is the negative binomial. And so how is the negative binomial different than the hypergeometric? Because at the very beginning of the video, I did say that both of them are related to that binomial distribution, the binomial experiments that we were doing, those fixed number of trials, independence between the trials, not replacing the item, and success and failure were the only two options essentially. So the difference here is that this one we do it a little different, and it's kind of called the negative binomial. So I'm going to write a little note on this one for a negative binomial, just abbreviating it. It arises from taking and fixing the number of successes. Now, when you did a regular binomial, you had a fixed number of trials. So we're going to fix the number of successes desired by letting the number of trials be random. So what you'll see a lot of times is that they'll phrase these questions for the negative binomial in a way where they'll say, I want to have 5 successes, and the probability of success is this. Then it'll ask you, what's the probability I needed 12 items to get that to happen, so that the very last thing I do, I'm going to then get that last success. So you're really phrasing this more as your random variable X is going to stand for the number of failures that precede the rth success. say precede instead of proceed. The rth success, that last success that we're looking for. Okay. Now, there is also a PMF for this. It's negative binomial, so NB, and you have two parameters that support our variable X. We have R, which is that how many successes are we actually looking for? And we need the probability of success actually happening. So we need our P, again, kind of related to the binomial experiment. And then this one is a choose formula, so it's combination. You have how many failures did I have to have plus how many successes did I have minus 1, choose number of successes I want minus 1. And then you times that by the probability of success to how many successes I'm going to have times the probability of failure, which is 1 minus P, to how many failures I have in total. So that's the formula for that negative binomial. And it is supported in a kind of an open-ended support because, you know, is it possible it took you 50 times before you got 7 successes? Yeah. Is it possible you got all 7 in the first 7? So it's left, remember, in a random, the number of trials is not fixed anymore. So that's kind of how the negative binomial works. Now, just briefly, I wanted to talk about geometric. The geometric distribution is related to this negative binomial. So when we define the negative binomial, we're saying the number of failures that precede the rth success. So our X in our formula, when we're calculating these, it's got to be how many failures did I have before I got to that last success. If you define your, say you define it as a Y instead, and you say, what's the number of trials that I had to go through, which is kind of X plus 1, because we stop at the failure right before that final success when we do a negative binomial. So when we call it a geometric, we're going to be doing, okay, I want to know how many trials that actually took. So that is a special case of that. So it's when your R equals 1. Okay, so that is when you call that the geometric distribution. Okay. All right, so, and again, we don't really do as much with that one. There weren't even really many questions in the homework for anything other than, I think you had some in your concept check that maybe asked you about the geometric, some of those multiple choice ones. And that can be found if you want to reference it. It's on page 129 and 130 in the textbook. It's also, I believe, mentioned in the PowerPoints. So we're going to focus on this negative binomial right now. So for this one, it says the probability that a randomly selected box of a certain type of cereal has a particular prize is 0.2. So that's our probability of success. I can go ahead and write that down. Have the prize. We're measuring, obviously, prizes is our measurement here. Suppose you purchase box after box. So not a fixed number of trials. We're just going to keep purchasing boxes until we have obtained 3 of these prizes. So notice how that's worded. We want 3 successes, but we don't know how long it's going to take us to get there. What is the probability that you purchase X boxes that do not have the desired price? So in other words, they phrased this as that number of failures that precede that final success, because we will still have the first 2 successes in the process of drawing these boxes. It's just, what's the probability that we have to purchase all of these failed boxes that do not have the desired price? So negative binomial, and then remember, we're only supposed to have 2 things after that. The R, which is the number of successes that we'll get to at the very last pick or draw, and then the probability of success. So it's going to be this one right here. So negative binomial of variable X with 3 successes total, and the third success is the last thing we do. And remember, that is 0.2 probability of success of getting the actual prize. Now, then they throw this little curveball at you and how they word this. So this is where these get a little tricky and why I wanted to do one of this. It says, what is the probability that you purchase 5 boxes? They didn't say 5 failed boxes or 5 boxes without the desired prize. We want to know 5 boxes total. So if we have 3 successes, where the last one's a success, of course, that means we're going to have 2 failures, because they just said 5 boxes. Okay. So this is going to be the formula NB where I have 2 failures before I get to that third and final success, and my probability of success is 0.2. So we're going to plug this into the formula, and that's going to be, and this is, by the way, if you wanted to write what is the probability here, it's probability that x equals 2, not x equals 5, because we're asking for failures when we reference it, number of failures that precede the rth success. So I'm going to write out my formula. It would be 2 plus 3 minus 1, choose 3 minus 1, times probability of success, and the number of successes is your exponent. Probability of failure would be 0.8 then, and that is going to be the number of failed boxes we got. So that's the 2. So that works down a little bit to 4 choose 2, and then that would be 0.008 and 0.64 if I use my calculator. 4 choose 2 is 6. You can use your calculator button, or you could do factorial expansion to get that. So if I multiply all that out, I'm going to get, rounded to 4 decimal places, 0.0307 for this one. Okay. What is the probability that we purchase at most 5 boxes? Okay, so they've worded this a little different. 5 boxes still means 2 failures because we want at most 5. So that's going to be probability that we have 2 failures or less. So we're actually doing, you could have our max number of failures could be 2 and 3 successes. We have to have at least the 3 successes. So the options here are, you got 5 boxes, which means 2 failures, 3 successes, or you got 4 boxes, which would be 3 successes, 1 failure, or you got 3 boxes only, which means all 3 were successes, because you have to have that third success to stop drawing boxes. So that's why it's less than or equal to 2. And the way you can do this one is you can do a summation of all of these NB PMF formulas. So I would have the summation as x, which is my failures, go from 0 to 2 of my formula NB, negative binomial, x, 3, and then 0.2. I'm going to go ahead and write what that would look like. So x equals 0 to 2. And then remember, we're going to write what this formula looks like with x instead of a 2 in for that first spot. So that's going to be x plus 3 will still be r, and minus 1. So that's going to be plus 2. R minus 1 is still going to be just 2, because that we don't know x right now. X is kind of unknown. It's going to float between these numbers. And then we have our 0.2 to the r, which is 3 successes. So that's still 3. And then 0.8 to the unknown number of failures right now. So you can pull out the 0.2 to the third, since that's just a constant. And then this means we're going to summation on x equals 0 to 2 of x plus 2 choose 2 times 0.8 to the x. So I'm going to have my 0.2 to the third out front, and then I'll have a bracket. This will be 0 would be 2 choose 2 times 0.8 to the 0, plus, if I put in a 1, that would be 1 plus 2, so that'll be 3 choose 2 times 0.8 to the 1, plus my last one is plugging in a 2, at least it's a small summation. 2 plus 2 is 4 choose 2 times 0.8 to the second. So if I work this out, this will be 0.008. 2 choose 2 is just 1 times anything in 0 powers 1. So that first guy is a 1. 3 choose 2 is 3. You can do your calculator. If you know that, that's fine. Times the 0.8 is going to be 2.4. Oops, did not mean to write the end of my parentheses yet. And then 4 choose 2 is 6 times 0.8 times 0.8, or 0.8 squared. That's going to be 3.84. And again, I used a calculator for all these. Do not know them all off the top of my head. If we add those 3 together and then multiply by 0.008, we get 0.0579 to 4 decimal places. Okay. How many boxes without the desired prize do we expect to purchase? Well, this then asks the question, what is the formula for expected value for a negative binomial? And that is on page 130 in the textbook. If you're looking for all of your formulas, I believe they're also all in our PowerPoints. But the expected value when you're doing a negative binomial that has the PMF as we've defined is going to be R times 1 minus P over P. So that is number of successes desired times the probability of failure, which this case was 0.8, divided by the probability of success. And that comes out to 2.4 divided by 0.2. That is 12. Now, this is number of failures, right? Because it says how many boxes without the desired prize do you expect? Because remember, our variable X is counting the number of failures it took to get to that R success. So when you calculate this, a lot of times students think that's how many boxes you've totally drawn. That is not true. That is just the number of failed boxes that we should expect. The last question asks us, hey, well then how many boxes did you buy? If you're at that or should you expect to purchase? Well, if you're going to have 12 failures to get to that final success, that means along the way, you already had 2 of the successes intermixed within those other ones, but they didn't get counted because this is the failures only. Then you get that last box as well. So you just add, this is our failures, we add the number of desired successes we were supposed to have, and that gets us how many boxes we purchased. So it's 12 plus the 3. Okay. So that finishes up that negative binomial one. Okay, for number 3, and I believe this is the last one in 3.5, it says a family decides to have children until it has 3 children of the same gender, assuming probability of boy and probability of girl are both 50-50. What is the PMF or probability mass function of X equals the number of children in the family? The only reason I put this one in here is because I didn't know when you're looking at your ones in WebAssign if they would do something similar to this, because sometimes they'll regenerate the tables a little differently. But they kind of have set this up for you without you having to think through like what the X's should be. And I do have a little bit of an issue with that because they've included 6 and you don't necessarily need it. So I think this would throw you off if you saw this in like homework assignment. Because we're going to just kind of, this is supposed to be sort of like a negative binomial, but the way they've defined X doesn't fit the mold of the negative binomial. Because we're kind of saying, okay, we need 3 successful gender matches in a, we need that last gender, that last child to match the gender of 2 that already came before it. But X needed to be defined as the number of failures. And that's not how it's defined. It's X is the number of children in the family. But we can reason through this. We can talk through it. So the probability that they have 0 children in the family, well, if they're going to keep having children until they have 3 of the same gender, this is not going to happen, right? That's 0. They haven't had any children. Probability of X equals 1. Also, they haven't met their goal yet of 3 children of the same gender. So the probability they're going to stop at 1 is also 0. Same thing for the probability equal to 2. If they are able to have children without any issues, of course, we're kind of assuming that, and they want 3 children of the same gender, they can't get that if they've only had 2 children. So those are all impossible measures here because they don't actually reach the goal. Now, when we get to 3, it becomes a different story because there's 2 ways that they could have achieved this. And it's they could have had the probability that they actually got all 3 girls or they got all 3 boys in a row. So just those 2 specific scenarios. Now, when we have an or, we add the probabilities together. So the probability of girl, 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 it's going to be the same for both of these because the probability of having a girl and having a boy are both 50%. So for this first one, it's 0.5 times 0.5 times 0.5 because the gender of your first child is independent of the gender of the next and the next and the next. So that would be for all three girls, and then 0.5, 0.5, 0.5 for all three boys. So this is 0.5 to the third plus 0.5 to the third. Type that into your calculator and work it out. You're going to get 0.25 once you've added them together. So there's only a 25% chance if they've had 3 children in a row that they're all three the same gender. Okay. Then we get to 4. And things get a little more complicated. And again, if we could use the negative binomial, if it was defined correctly, if we could somehow discuss the number of failures and how that works, but it's kind of like, it's a little hard to imagine how that works. So it's easier to reason through this one. So if we're doing 4 children, they've had 4 children, you can't have all 3 girls at the beginning because then you would have already had 3 in a row. So you could have 2 girls and then a boy, and then the third girl. Or you could have a girl, a boy, and then 2 more girls. Because again, the third girl has to be the final choice. Or you could have had a boy followed by 3 girls. Because again, we're not getting to that third girl until the 4th choice. So those 3 things are possible, or it could be reversed. If you're doing 3 boys, it could have been boy, boy, girl, boy, or boy, girl, boy, boy, or girl, boy, boy, boy. Now, all of these are going to be 0.5 times 0.5 times 0.5 times 0.5, which is to the 4th. If you multiply them all together, and they're all independent, it's because this probability is the same. But there are 6 combinations. So this is 6.5 to the 4th. Okay. And if we work that out ends up working out to 0.375. And then you're thinking, okay, starting to get it. And then we ask, well, what happens if it's 5? And that would be really tedious to try and list that out, to just make sure you didn't miss any possible combinations of how could the 3 girls and or the 3 boys work. And you also have to make sure you didn't put the third girl before the 5th actual final draw or having a kid. So that's a little bit more complicated, but this is the thing that's true about this. This is the last possible choice. Okay, because it's guaranteed. You are guaranteed if you've had 5 children that you have had 3 of the same gender. Okay, if you think through that for a second, that makes sense, because even if you alternate kids like boy, girl, that 5th one is going to be the third boy. Okay, so this is the last possibility. This is the max value you could get to. So I don't like that in WebAssign they put that 6th column there, because that makes you think that's an option. So this is actually not needed. It's 0, but this one is. So if you don't want to try to figure out all these pieces, since we know that a probability mass function has to sum to 1, because if they get to 5, they've had 3 of one gender, they're going to stop having children. Okay. This is got to add to 1. So we just do 1 minus 0.25 minus 0.375. So that is why this one is also 0.375. Now, if you wanted to try and write out all the possibilities, you could. I just think it would be wasting a lot of your time. And sometimes it helps to think through these things and think, could I even go beyond this? And no, because as soon as you've had 5 children, you absolutely have had, no matter what, you've reached the third of one of the genders. Okay. All right. And then we're looking at number 4. We're now getting into section 3.6, the Poisson process and the Poisson distribution. This is a little different than what we saw with like our binomial experiment, because hypergeometric and negative binomial and geometric, they were all based off of kind of that binomial type experiment with successes and failures, and the trials being independent. We kind of had a lot of similarity in some of those setups. Poisson is not based on a simple experiment of trials. It spreads probability over all non-negative integers, so there's an infinite number of possibilities. We do need our probability distribution still to sum to 1. So we have to have the probability, and this one is got a parameter mu, and it is going to be related to our mean. Excuse me, it's our expected value of our mean. And so we know this has to equal to 1 for this to be a legitimate probability distribution. And the way that works for this, because I'm going to write what Poisson actually looks like in just a second, it's you have to go and use some calculus, which we're not going to make you prove, but this should sound like a familiar phrase from your calculus 2, I believe. We do Maclaurin series. Those are summations of the expansion. I don't know why this keeps jumping around. Of e to the mu. So you can look that up if you want. If you just feel like you need to review that part of calculus, go ahead. It's not required. But let me give you what the probability distribution actually looks like for this. So our PMF, which is our probability mass function, is P of our variable X, which we'll define what that means in just a second, and our parameter mu, and it works out to be e to the negative mu times mu to the x all over x factorial. So if you look, and mu has to be greater than 0 for this, and our x's can go from 0 to infinity on the integers. Okay, so our support. So that's the PMF for our Poisson distribution. Now, what are they used for? What are they helpful for? Well, we use, especially when we get to the Poisson process, we use it a lot for looking at things happening in a specific interval of time. So you'll notice this talks about particular length and certain things happening in a particular length of a pipeline. So the video I posted from Professor Lemus, because I don't want to expand this video hours and hours, had some really good examples of what actually makes up a Poisson distribution. So you'll want to reference that as another place to go look for some more examples. Our binomial experiment can approach Poisson when we look at the limits, where our little n is large and our p is small. In the textbook, they say for our class textbook, because I've seen in different textbooks, sometimes they set parameters more conservatively, but the n, our sample size has to be greater than 50, and n times p, which is the mean of your binomial experiment, has to be less than 5. So that's the only time you can look at letting the binomial experiment, I'm trying to say this backwards. It's very late. Binomial experiment approach the Poisson. That's what I was trying to say. Okay, so we're going to look at this and kind of talk about why it's Poisson. And it actually tells you in there that it is. A lot of times they will. It says the article expectation analysis of the probability of failure for water pipe supply pipes proposed using the Poisson distribution to model the number of failures in pipelines of various types. Suppose that for cast iron pipe of a particular length, the expected number of failures is 1. Okay, so in that specific interval or particular length, the expected number of failures is 1. Very close to 1 of the cases considered in the article. Then X, the number of failures, has a Poisson distribution with the mean mu being equal to 1. We're going to round all answers to 3 decimal places, and we're going to show you, I'll have to switch to my Google for this because I couldn't pull up the appendix on my computer down here for some reason. But I'll show you kind of how we can read the probability table for this. So we're wanting to know the probability that we have big X less than or equal to 5. So remember, number of failures less than or equal to 5. And that formula, remember, is going to be I'm going to write this down over to the side. Mu is 1. So my formula is Poisson probability is going to be a variable x, so some x that we're looking for, with a mu of 1. That has the formula e to the negative 1 for our mu times 1 to the x over x factorial. So I always plug in my mu first and get this PMF so that I can then work with the probabilities. Now I can do these by hand. So if I wanted to do probability of 5 or less, let's say x is less than or equal to 5. Let's write it correctly first. That x is less than or equal to 5. I would need to do these individually because this formula is not cumulative right here, whereas the table is. This would be individually what each of those equals. So when we look at this, this would be probability of a Poisson that we have 0, because less than or equal to 5 can start with 0 up to 1, plus Poisson of 1 with a mean of 1, plus Poisson of 2, 1. So we would just keep going, okay? And that means I'm not going to write all of these out. Well, I'm going to write this part, plus Poisson of 5 to 1. But essentially, if I wanted to compute this by hand, I would have to do e to the negative 1 times 1 to the 0 over 0 factorial, and so on, okay? So if we were crunching it by hand, we would have to individually do each of those pieces. Now, if you have the cumulative Poisson probability table, what you can do instead is convert this to the correct notation for that. So probability of x being less than or equal to 5, when we look at it on the table, it's called the capital F, and then it's our cumulative function, essentially. So cumulative, where we have our x followed by our mu. Whatever you put in here for x, when you look this up at the table, it's going to tell you everything from 0 up to that value. It's going to give you all those accumulated probabilities and that one number. And then this would be at a 1. Now I'm going to pull the table up and share it because this one's a little funky to read. And let me get to the right one. The cumulative binomial. So it starts right here, which is hard to see. Cumulative Poisson probabilities. It's a summation from 0 to x of e to the negative mu, mu to the y, and then over y factorial. So we're summing from y up to our x. So that's why it's accumulating, okay? So you find your mu first, and this first table goes from 0.1 to 1. The table down here goes from 2 to 20, but it doesn't get every single value. So there's some skips between 10 and 15 and 15 and 20. But you'll see that there's these accumulating probabilities here that always end in 1 because they've reached the end of it. This 0 is the only one that gives the exact probability of that specific value. If you're at 1, you've added the probability of 0 plus the probability of what happened at 1. So for us, we were at, you're going to find your mu is 1 and your value for x was 5. And sometimes this is hard because you have to kind of imagine drawing the line over. So that's 0.999 is where those meet. So let's go back over to our other page. And those meet at 0.999. Now for the second one here, it says use the PMF formula because they're asking for an exact. So we don't want to go to the accumulating table if we don't. It's actually harder to do an exact on the cumulative table. We are going to do that for the second part of this, but you have to think a little differently. So if I want to do this, this would be P of 2 with a mu of 1, and we just directly plug into our PMF. This is e to the negative 1 times 1 to the second over 2 factorial. I worked that out earlier and I got that that was 0.184. Now I should still get the same thing here, but the problem is in the table, they're accumulated. So if you want the probability that X equals 2 from the table, you're going to use, remember, your F to represent the cumulative distribution function there that adds up all those probabilities. You're going to need to say, okay, I want to have everything from 2 and below, but that's too much. I only want 2. So you go one number underneath and subtract that cumulative probability. So essentially, you're saying 1 accumulates 0 and 1, 2 accumulates 0, 1, and 2. So if we subtract those, we would just be left with the probability at 2. And if you look these both up in the table, I'm not going to flip back and forth on each of these. But if you look them up, you get 0.920 for the first one, minus 0.736 for the second one, because that's mu of 1, and we have our x of 1. And then when we subtract this, this is also 0.184, like we expected, because those should match since they were the same. Now, this is a little different. What if we want to do between two values? And again, I would want to use the accumulating table instead of, but I mean, it's not that bad. I could do equal to 2, equal to 3, equal to 4, and use my PMF actual formula for that. But if I've got the table handy, I would use the table. So we're doing 2 less than or equal to x less than or equal to 4. The key with this one is about the endpoints, because when you look up something in the cumulative table, it includes that actual endpoint. So if I start with the bigger one, which is 4, okay, this is directly related to the probability that x is less than or equal to 4 with the equal to. If I do f of 2 and then 1, that's actually not going to be correct, because including the 2 means I'm including that probability in this value, and I would be subtracting it away from this. I want to actually keep the 2 in my answer because it's included here. So we want the probability that x is actually just less than 2, because that's all we want to subtract off. We want to subtract off the case of 0 and 1. So to make that happen, you actually go down a number because you don't want to include the accumulated values for 2. So notice I'm doing f of 1 with 1 as the mu again. So this one ends up being, from my chart, this was 0.996 for the 4 to 1 minus 0.736, which we'd already seen that one up above. And this ends up being 0.260. And then what is the probability that x exceeds its mean value by more than 1 standard deviation? Okay, all of these that we've done tonight on my really long video, I've always left the expected value formula until we actually encounter it. Expected value for a Poisson distribution, it is the mean. The mean mu is already a parameter in your problem. And also, it's your variance. So it is in the Poisson process and the Poisson distribution, it functions as both. So everything is essentially the mean. It's based off of that. Now, when we go to look at this, then if we want we have to read this. What's the probability that x, our variable, random variable, exceeds its mean value by more than 1 standard deviation? Okay, well, if your mean is 1 and you add 1 standard deviation, which is also 1, because remember our mu was 1. So E of x plus 1 standard deviation, which if variance is mu, and it's 1, that means standard deviation is also 1. That may not be true for every single one, so be careful there. If my mu had been 2, then it would have been square root of 2. So I would have had a square root of 2 here. But because it was 1, this for our mu, it essentially is still itself. So we want to have standard deviation here, which is why, because of that being square root of 1, it's still 1. So we need to be 2 above, that's what we're looking for, that probability of X being greater than or actually it doesn't even say greater than, it's just more than. So greater than 2. So how could we calculate that? Well, you could do 1 minus X less than or equal to 2, since we have accumulating probabilities. 1 minus the probability that we are X less than or equal to 2. If you look up 2 with a mean of 1 in your table of cumulative probabilities, that is 0.920. So if we subtract that, that would be 0.080. Okay. So Poisson distribution. Now, one of the things that we see a lot with Poisson is something called a Poisson process. Most of the time, and if you look in the textbook, most of the examples, they're like time intervals, looking at things like, one of the examples in the book was like, suppose pulses arrive at a counter at an average rate of 6 per minute. So then they have this parameter alpha called 6. And then you want to know what happens in a half-minute interval. We're going to want to know that probability, or that there was at least 1 pulse received. So you're looking at these time intervals. And when we talk about that, there's also other processes that can model that don't actually have to do with time. This one has to do with kind of like area. So acreage, which is an area. So a Poisson process, just to give you a little background on kind of what we're talking about. And y'all have to excuse me if I'm all over the place. I have been sick all week. This measures and looks at the occurrence of events of some type over time, which for us, this one, they're telling us to model it with a Poisson process, we're kind of doing it over area instead of over time. So like, for example, the number of events during a time interval of length t is a Poisson random variable parameter. Mu is you're going to have a parameter alpha usually involved in this, is going to be alpha times t, which would give you the expected value over any time interval. So you would just say my alpha value times the interval of time that I'm looking at, or for us, interval of area. And then the just expected value in 1 unit of time would just be alpha. So there is a formula for a Poisson process. It is P of sub k of t equals e to the negative alpha t times parentheses alpha t to the k over k factorial. Now alpha t right here, I just said that a minute ago, this is the mean. It is going to be our expected value over any interval of t. Okay, so essentially it is still the same formula. We're kind of talking about things in terms of these little subintervals of time. And like I said, this one is Poisson process, but they're using kind of acreage instead of, they're using area. So it says, suppose that trees are distributed in a forest according to a 2-dimensional Poisson process with a parameter alpha, the expected number of trees per acre. So they're already telling us the expected number of trees per acre. So notice expected value over any interval of t, where t for us is acreage. So that's 60. So we know our mu right here is going to be 60. And that's per acre. So that's per 1 unit. So this one actually is just directly alpha. Okay. So this is a unit. So you don't even have to write mean on this one. because this is for one subunit. Now, if we want to know what would we call mu for any acreage, so not just one unit of acre. So like what if I wanted to do a quarter acre, a half acre, 50 acres? The formula for our expected value there is going to be alpha times T. So this is trees per 1 acre. That's what alpha stands for, that parameter. Now, this first question then is going to make us immediately calculate a mu based on a different measure of area. Okay, we're still talking about an acre, but we're not doing 1 acre. So it says, what is the probability that in a certain quarter acre plot? So quarter acre, what would we expect in a quarter acre? Well, we would expect the 60 parameter that we had in a 1 acre, and we're going to cut that by a quarter of an acre. Okay. So if this was time, say this was, say this was for a 1 minute time, this alpha was for 1 minute, and then they wanted us to say, well, what would happen in 50 minutes? You would take your alpha and times it by that conversion. Okay, so this is any unit of time or any unit of area for us. So that's going to come out to 15 trees per quarter acre. Now that just gives us our mu. Okay, that gives us our mu for our formula. It's going to be our exponent here and the base for that k. The probability they want us to do is at most 14 trees. So probability that we have x less than or equal to 14, where we know that we're wanting a cumulative answer here. So we're going to use our F accumulating formula, and we want 14 or less, so that's what this value is, and our mean was 15 trees per the quarter acre. Okay, now if you wanted to plug that into the formula, if you were doing just exactly 14 trees, you would use, remember, e to the negative 15, because that would be our mean for that specific quarter acre. We'd have 15 to the 14th over 14 factorial, but we do not want exactly 14, we want at most. So that's why we're using this. So I'm going to switch back over real quick just to show you again the chart, since this one's a little different. We would have to go down and find mean of 15, go down to 14 for the x, follow that over. That is 4.66. Or 0.466. Sorry, said my point in the wrong place. So there's my probability using a Poisson process where we took alpha, which was for 1 acreage, and then we converted that to an expected value for a quarter acre. And then we used our cumulative Poisson probability chart. Okay. Now, the next question says, if the forest covers 75,000 acres, what is the expected number of trees in the forest? Well, this is again finding a mu for that specific area. So this would be just mu equals 60 times 75,000. And it's going to be really big. That's going to be 4,500,000 trees per that 75,000 acres. They didn't ask us to write all that out, but it's helpful. So 5, 0, 0, and then 0, 0, 0. Okay, last part for tonight. Suppose you select a point in the forest and construct a circle of radius 0.1 miles. Let X equal the number of trees within that circular region. Okay, so our area is going to be, an acre can be cut many different ways as long as it adds up to the correct square miles. Or I should say the correct ratio of that, which is why they gave us a hint here. We want to know what the PMF of this specific one is. To be able to find that, we have to know, to get our PMF, we have to know what alpha times T is going to end up being. So to be able to find this, you got to first talk about how do I know what the area of this region in the forest is? They didn't give it to me in acreage, which is what all of my other ones were, and my parameter was in acres. So I need to take the area formula of a circle, which is pi r squared, and I'm going to put in 0.1, and that's going to end up being miles squared. We're going to put 0.1 in for that, and that gives me an area of 6.4, and we're going to leave the pi there for now, pi miles squared. Okay, and then I had a hint. 1 square mile is 640 acres. So I need to convert this area in square miles to acres. When you do a conversion, you want the same unit that you have on top to be on the bottom, so it'll cancel, and the one you desire will be on the top. So this is 1 and 640. So we're going to be multiplying 6.4 pi times 640, and we're going to leave the pi alone. We're trying to get an exact answer. So 640 times 6.4 is 384 pi acres. Okay, so that helps me because remember, I can now talk about, we can talk about now that we've converted this to this piece, and we multiplied by, yeah, we've turned it into acres. I'm just triple checking myself. Oh no, I did this wrong. Let me back up. That is not 6.4. I jumped the gun on one of my numbers. Okay, back up. We are going to get that answer at the end, but I skipped a step. This is what happens when you record at night. Hopefully, if you're watching along, you're just like, poor Miss Metzger. 0.1 squared is not 0.64. I bet y'all are all scratching your head. It's 0.01 pi. I was doing a step that I needed to do, but I had done it too soon. So this is going to be 0.01 pi miles squared. We are still going to times it by 640 to turn it into acres, which gives me the 6.4 pi I wrote down a minute ago. That's the acreage. Okay. We still have to turn that into, remember, an expected value. So for this many acres, what's the expected number of trees? So that's what I was missing. So mu is going to be alpha, which is 60 still, because that was our setup for our parameter, times the 6.4 pi for the acres. Okay. So this is going to be, remember, our trees per acre. So that's where we get the 384 pi. And that is trees per 6.4 pi acres. Okay. So once you have your expected value for our time interval or your area interval, we're going to plug that into our formula here. So our PMF is going to be E to the negative of that, alpha times T. That's what this is. So that's going to be negative 384 pi times 384 pi to the K, which for us is going to be X, because we have an unknown variable for our probability right now, over X factorial. And you can put the E on top with the other part, that doesn't matter, as long as you don't put it in the denominator with the X factorial. Okay, so hopefully this is starting to be more helpful. I still have one more series to do for this week. I don't know that I'm going to do it tonight. It might not happen until Sunday evening, but you've got the 3-3 and the 3-4 and 3-5 and 3-6. So that should help you get those homework sections done. Remember, I extended the concept checks until Monday for this week, just because there's some integration that pops up in that part 4. Please reach out to me if you need any help with that. And then it's in the chapter 4 stuff where the integration pops up. So reach out if you need help with that. And then the other thing was, oh yeah, the web assigned homework has been moved one more day back to Wednesday, just to keep that from not being too close to each other. So you have a little bit of time to get through these, and let me know if you have questions. I'm here to support you. Have a good evening.